take a look at the free radical halogenation reaction. It's a one electron transfer reaction. And what I want to look at first is just the observed reaction. So remember, that's like a snapshot of what's going on. So what we're going to look at here is something rather simple, and we'll get more complicated, but here's methane. And to this, let's add chlorine. Okay. Now, what's going to happen here is that one of those H's on the carbon, so, right, one of those H's here, is going to be replaced with a chlorine atom. So what that's going to leave you with is an H atom, right? And only one chlorine reacts here. So the other chlorine will go to the hydrogen, so you form hydrochloric acid. Now, this reaction just doesn't occur if you just mix these two things together. What we have to do here is we have to use heat, and sometimes we indicate that with this little triangle in OChem. Or most often what you're going to see is light. And that light is indicated often by writing H nu. It's a photon of light. And it turns out that it's a certain wavelength of light that helps get this reaction to occur. So a couple of important points as we look at this and before we get into the individual mechanistic steps. So number one, this requires heat or light for initiation. That means the reaction won't start unless you initiate it. The other thing is that the wavelength of light is typically blue light, and that's absorbed by the chlorine gas. So something's happening in this reaction where chlorine needs to have a homolytic bond breaking before this reaction occurs. And the other thing here, this is important too, is that this is a chain reaction. So during a chain reaction, lots of products are formed from the absorption of only one photon of light. Okay, now the other thing that I'll point out is that the reaction may continue to form carbon tetrachloride, but for us, we're really only going to monohalogenate. Okay, so that's what we're going to be thinking of when we go through and determine what the products are of a reaction. Now, the mechanism of this thing has three steps. There's three elementary reactions in this. The first is initiation. In the initiation step, radicals are formed by breaking that bond homolytically. Right? So let's look at chlorine. That's what we started with a minute ago. So let's put in here chlorine, and then let's just put in all of our lone pairs, just like so. Now remember, we said that this requires a photon of light. So I'm going to write up here a photon, or H nu. Okay, so that light comes in, and what happens is that the right energy comes by and it helps us break this bond. So we use these little fish hook arrows, remember, to show electron flow for a radical. Now what we form here is chlorine radical. Now we get two of them. It happens twice. So I'm just going to write a 2 there rather than write them out 2 times. All right, so 2 radicals are going to form here. That's our first step. Okay, so this initiation steps are often very rare. So about 1 for every 10,000 propagation steps. So remember we said in a chain reaction, technically one step or one initiation can make this reaction just go on and on to completion. So why only 10,000? Well, we'll talk about that, and it has to do with step number 3, which is termination. Now for our propagation step, there are 2 steps for our propagation. So propagation is a step in which we need to kind of keep like the hamster wheel moving around and around and around and around and around, right? We need to keep feeding it. Otherwise, the reaction would stop. So let's just look here at propagation step number 1. It's a really cool kind of mechanistic step here. So we're going to take here methane. right? And to that, we're going to add one of those radicals that formed up above in that initiation step, right? Remember that form there. All right, now these things are floating around in solution, and at some point in time, chlorine comes over and hits the hydrogen atom of methane hard enough that we see an electron flow. So what's going to happen is this thing comes over and kind of hits the hydrogen, and when it does so, we see an electron flow that looks kind of like this. And then that other remaining electron, remember there's two, right, and that carbon hydrogen is going to come over and live on carbon. So what we're going to form here is our H radical with 1, 2, 3 hydrogens. That's a methyl radical. And then we form hydrochloric acid, HCl. Now sometimes you may see this written out, the chlorine written out like this. So often we'll write it out like that. And we understand that there must be 3 other lone pair. And the same thing over here, sometimes we'll see this just written like that. And again, you understand the lone pairs need to be there. So in propagation step number 2, we're going to take that methyl radical and we're going to add chlorine. And we're going to get chlorine floating around. It's going to come over and it's going to hit that radical, and we're going to see an electron flow that looks something along those lines. That'll give us our H connected to a carbon and our chlorine just like that. And then look what we've made. We have made another chlorine radical. All right, that's important. All right, so these 2 steps repeat many, many, many times. And the majority of the product is formed by just these 2 steps. The vast majority. Now the other thing that I just wanted to point out to you here is that here we've made this radical. Now that radical can feed back in to propagation step number 1, right? So what happens is this, is we get that first initiation occurring, right? Make a radical, and then that radical comes over here and reacts and forms HCl and our methyl. Right? That methyl comes down here in our propagation step number 2, right? Now, as we do that, our chlorine then reacts. So Cl2 reacts, and it comes over and it gives us our product. But then conveniently, it makes another chlorine atom, right, a radical. And then that goes back and feeds into propagation step number 1. So that way, this reaction goes around and around and around and around like this over and over and over again. In theory, it could occur, right, with just one radical from the very first initiation step. This would occur until there was no more methane. But it's not perfect. So the reason why it's not perfect is because the termination step can occur. And these are rare also. So in our termination step, they're rare, about 1 for every 10,000-ish or so, right? So what happens in termination? Termination basically is where we kill radicals. So all the radicals that form can combine in ways that we don't anticipate, right? So in a reaction vessel, it's not like we can create some type of a line where, hey, methane reacts with this radical and then this happens, and you wait over there and then come down here and react with chlorine. They're all just moving around in solution. So for example, the chlorine radical could recombine with another chlorine radical, right? That's something that could happen. Could react with another chlorine radical, right? Putting our arrows in. That would give us Cl2. Well, that's one way to kill things, right? What else? What if we took our CH3 radical, right? So we have our CH3 here. So we could also take our CH3 radical, right? And we could combine that with the chlorine radical. Right? So that would give us this. So that would give us CH3Cl. Now that's your one of your products, but it's not, we didn't get it by the correct mechanism. The methyls could also combine. So CH3 could combine with another CH3. Right, so arrows, there we have it. And that would give you ethane in this case. And then the other thing that can happen is it turns out that these radicals can combine with the walls of the glass. Right, so your container wall. So chlorine radical or your CH3 radical can basically hit your glass, like the wall of your beaker or your flask, whatever you're dealing with, and bond to the glass here. So sometimes you'll see this written out as like the wall. So then what you would get is chlorine attached to the wall and CH3 attached to the wall. Right now, so it bonds then to the glass.